Okay, so let's prove this proposition. So let x and y be some connected, irreducible components of G containing the neutral element, and then their product xy. So I mean product in the sense of multiplication in the group. So it certainly lies in the closure and is irreducible as the image of an irreducible product variety. But we have x lies in this product, and also y lies in this product. So since they were irreducible components, it necessarily means that x equals xy equals y. Okay. Also, it implies that the product of any component with itself, well, again, it means multiplication of x times x is x. Okay. Also, we see that x inverse also contains the neutral element, and hence x inverse is equal to x, and hence finally x is a closed subgroup. Now again, similarly, for any G, the conjugation x on this irreducible component, so x is normal. Now the cosets of x gx are irreducible components. Sorry. And hence there are only finitely many of those cosets. Sorry. No. Okay. So it means that the complement G without this G naught, that is x by definition, is the union of finitely many cosets, and hence it is closed.
Можно еще раз, почему конечное число?
Yes. It is just a property of algebraic varieties, that an algebraic variety has finitely many irreducible components. Okay, so I assume some basic algebraic geometry facts, and I will assume more and more as we go.
Okay, thank you.
Welcome. Okay, so the complement is closed, and hence this neutral component is a connected component. Okay, and similarly, any subgroup H closed of finite index is closed and open, and hence necessarily contains this neutral component. Okay, so we have proved the first proposition. So now let's go on. We'll need the following lemma. So suppose we have two open dense subsets, U and V in G, be two open dense subsets, such that no, nothing else. Just then their product is the whole group. And the proof is very simple. Just consider translate of one of them. So since V is open dense, its inverse is also open dense, and its translate is also open dense. So the intersection with U is not empty, and hence G lies in UV. Okay. Now the second proposition is about any subgroup not necessarily algebraic. So for example, in the additive group, I could take an infinite subgroup generated by any element. Yeah, just the multiples of any number, and it's not algebraic subgroup, but then I take its Zariski closure. Okay, so then I claim first that H bar is an algebraic subgroup. And second, that if H contains an open subset of H bar, then they just coincide. Okay. So once again, the Zariski closure of a subgroup is also a subgroup, now algebraic subgroup, and if H is somehow if H contains an open subset of H bar, then they coincide. So let's prove it. So take an element in our subgroup. Then we have then if we translate H by G, certainly nothing happens, and it lies in the closure, um, but it's closed. Uh, so H bar necessarily lies in GH bar, and also G inverse H bar lies in H bar, and hence H bar times. Again, this product means multiplication of the external product lies in H bar. Okay, and hence for any G in H bar, GH lies in H bar, and GH closure equals GH bar, and it lies in H bar. So uh, so sorry. So I want to conclude that H bar times H bar lies in H bar, but what I wrote before was only about H. Sorry, I just wrote not what I said. And again here there is no bar. Sorry, but now finally we conclude that it's closed with respect to product, and also the inverse of H bar is the closure of H inverse, so it's just H bar, and finally means that H bar is a subgroup. Okay, and now I have to prove this was A, and I have to prove that if H contains an open subset of H bar, then they coincide. So if U in H bar is open, and U is in H, then H is well, is a union of cosets of U, and hence it is open in H bar, and by the previous lemma, we conclude that H bar is the product of H times H in the same sense, and this H. Okay. Fine. And now let me prove what I announced before. About the closed subgroups. So suppose we have an algebraic homomorphism. Phi from G to G prime, some other algebraic group. We conclude that its kernel is well, just by definition, this is the preimage of the neutral element, is closed, and normal subgroup. This is evident, but also the image of G is a closed subgroup of G prime. This is interesting. And finally, the image of the neutral connected component of G is the neutral connected component of the image of G. Okay. So A is evident. Now, for B, we use Chevalier theorem. Namely, that the image phi of G is a constructible subset of G prime. That is the finite union of locally closed subvarieties. Okay, maybe you remember that for a projective morphism, its image is always a closed subvariety. For a fine morphism, it's not necessarily true. For example, say for a fine blow up, the image. So say if you have A2 with coordinates x, y, and it goes to another plane with coordinates whatever t, z, and phi of x, y is x, x, y. Then the image of phi will be 0.0, the origin, and the A2 without coordinate line like this. Okay, so it will look something like this. You throw away a line and add a point instead. Okay, so it's a typical constructible subset. So we know that by Chevalier theorem that the image of any algebraic morphism is a constructible subset, and hence it contains.
Сейчас это для... В
Yes.
каком случае это верно? Там, для конечного типа? Или...
Oh yes, for finite type, yes. For any algebraic morphism of algebraic. Well, algebraic varieties somehow, by definition, have finite type. So for any morphism of algebraic varieties, the image is constructible. Okay. So then the
Но мы в
image.
определении не сказали, что они там конечного типа.
Yeah, the spectra of algebras of finitely generated algebras. So I should have said it. Okay, so we assume everything of finite type. Okay, so phi of G contains an open subvariety of its closure. And so by the previous proposition, we are done. Okay. So finally, about connected components. So phi of the neutral connected component is a closed connected subgroup of G prime. And it has a finite index in phi of G. Well, since G not had a finite index in G. So there we are. Well, maybe I should say that it follows by proposition 1. See, now implies what we want. Fine. Now, another notion we certainly need in our class is the notion of G actions. An algebraic group G on an algebraic variety X is an algebraic morphism A from G times X to X with the usual properties. And once again, if G is affine and X is affine, then we have the induced morphism on the rings of functions. Okay, and this equality that the functions on G times X is the tensor product of functions on G and functions on X. Somehow this looks very evident and innocent, but the very non-trivial results in a few moments will follow just from this, namely just from the fact that by definition, any tensor product is the sum of finitely many sums. Just from this, okay, the finiteness results all will follow just from this finite. Okay, so in particular, we get a representation of G in the algebra of functions on X, say sigma f. No, sorry, maybe I should say sigma of G acting on F. If we evaluate this at point X, then by definition, this is f of G inverse X, just the usual formula. But this is an infinite dimensional representation. And on the other hand, we can consider some finite dimensional representations. So a finite dimensional representation of G on V is called algebraic, or sometimes for strange historic reasons, maybe also called rational. If the corresponding morphism from G into GLV is algebraic. Okay. So then, for example, if X in V is a closed G invariant subvariety, then we get an algebraic action of G on X. And we will prove right now that any G action, algebraic, on an affine algebraic variety X arises like this. So there is a G equivariant embedding of X into V with G action here and here. Okay. Also, if G is acting on V, then certainly it gives rise to the action of G on the projectivization. And again, if we take a closed G invariant subvariety Y in this projective space, well, carries an algebraic G action. Okay, and again, it is true that any projective G variety arises this way. But the proof is much harder, and we will give it, but not today, but in the spring. Okay. So so let me prove this affine theorem. Yeah, that any affine algebraic variety can be equivariantly embedded into a G vector space. Mm. So in order to embed an affine G variety X into an algebraic representation, we need to prove the local finiteness of the action of G by this sigma on the algebra of functions on X. Yeah, that's how we argued a week ago. Yeah, because just take say finitely many generators of this algebra. So we assume all our algebras finitely generated, and embed this finite set into a finite dimensional G invariant subspace V star in this algebra of functions. And there we are. Okay, so it will induce the embedding of X into V.
Excuse
Yeah.
me. I might have missed a bit. So what's the statement that we are going to prove? Is it that any
The local
algebraic
finite.
action
Pardon me?
Is the statement that any algebraic action on a affine variety arises from a representation of our group, from algebraic representation of our group, or
so we are going to prove that any affine G variety X can be equivariantly embedded into a vector space with G action, like at the top line of this page.
Yeah,
okay, that's what we want to prove. And in order to do this, it suffices to know the local finiteness of the representation of G in functions in X. Okay, so we actually now we're going to prove this local finite. Okay.
Yeah, I see.
So this will be our proposition 4. That T of X is a locally finite G module mm, so maybe let me formulate what it means once again. So suppose given a finite dimensional subspace F in this algebra of functions, there is first of all G invariant subspace E containing F, also finite dimensional. Okay, but G invariant. And second, that F is G invariant if and only if the action morphism of F lends into functions in G on G tensor F. Okay. So the proof, as I promised, it will just follow from the finiteness of tensor product. So it suffices to take F one-dimensional generated by some function, and then we consider the action morphism on this function. This will be some finite sum, say UI tensor Fi. So UIs lie they are functions on G, and Fi's are functions on X. Okay, but this is a finite sum. Then if I act by some element G on this function and evaluate it at certain point X, then by definition, this is f of G inverse X, and this is the sum of UI of G inverse Fi of X. Okay, but then it means that all the translates sigma of G applied to F lie in the subspace spanned by those Fi's. Okay, and this is a finite dimensional space. So there we are. This proves A. Right? And this is somehow miraculous, at least to my taste. You proved a very strong statement just from nothing, from the finiteness of tensor product just by definition. Okay, now B. So if the action on our space lies in functions on G tensor F itself, then F is invariant just by the above argument, if you want, and conversely, choose a basis Fi of F of our finite dimensional subspace, and extended um, mm, to a basis like this, Fi, and also say Hi, um, mm, the basis of the whole algebra. Okay, so for element in our subspace, we have that the action on this element is a certain sum of ui tensor fi plus a certain sum of phi j tensor h j. Maybe I should call it j. Okay, and then the action of element g on f will be the sum of ui of g inverse fi plus the sum of vj of g inverse times hj. Okay, but we know that our subspace f is g invariant, so you cannot have actually the second type summands. So we know that Vj of G inverse equals 0 for any G, and hence Vj are identically 0, and hence the action of on this subspace F lies in functions on G tensor F. Okay, so that's what we wanted to prove. Okay, and now from this, again, almost for free, we will deduce that any any algebraic linear algebraic group is actually closed subgroup in some GLM. So theorem. Let G be a linear algebraic group, then G has a faithful algebraic representation. G is a closed subgroup of certain GL. And somehow this just justifies this name linear algebraic subgroup. It's a subgroup of general linear group. Okay, so proof. We consider the action of G on itself. In fact, it can act both on the left and on the right. So if we have a function in G, then there is the left action, lambda of G, f of x is f of g inverse x as before, and also the right action rho of g f of x is f of xg. Left action, well, left translation, right translation. So we know that our group is an algebraic variety. So in particular, the function algebra is finitely generated. So we can choose finitely many generators, f1, so fn of the algebra functions on G, and find a finite dimensional row of G invariant subspace E that contains all of those generators and is contained in the function algebra on G. Okay. Then the right action row of x on the function fi is a certain combination mij of x times fj. Okay. Well, maybe, I'm so sorry. I'm saying this. Maybe I shouldn't say it this way. Now that I find a finite dimensional, sorry. So we may extend this collection of functions to a basis of E. Okay, so I extended f1 and so on fn to a basis of E. So now these maybe they're called f1 and so on, f capital N, like this. Okay. And now the action somehow permutes all these big bases from I equals 1 to capital N. Okay. And now we define phi of x as just the collection mij of x, I and j run through our basis set. And this homomorphism from G to GL capital N, GLE. Okay, so we have to prove this is injective. If rho of x f I equals fi for any I, then fi of x equals fi of e for any I, and hence f of x equals f of e for any f in the function on G, right? Because those f's, they generate the whole algebra of functions, and hence x equals to e, the identity element. Now, well, certainly phi is an algebraic morphism, and say phi star from the ring of functions on GLN to the ring of functions on G takes so this is as we described before, the ring of functions of T I J with determinant inverted, and those T I J go just to well, just to M I J that were defined in the very top line of this page, and what else can I say? I think that's essentially it. Yeah. Say f I of x is the sum of mij of x, fj of e. These are just coefficients. So these matrix coefficients generate all the functions. Okay, so phi star is surjective from the ring of functions on GLN to the ring of functions on G. Okay, so it means that G is a closed subgroup of GLN. That's what I want to prove. Okay. Now we only have 7 minutes left, so maybe let me just announce what I want to do next time. So next time we will study some rational invariant. What does it mean? Sorry. So if G is not finite, then in general, well, say for a fine x with the action of G. Sorry, what am I doing? Yeah. So for a fine x, the invariants in the algebra of functions do not separate the orbits of G in X. Yeah, so our running example is G GLN, and X, it's Lie algebra, that the matrices, and the action is the adjoint action. Then we know that the invariants are generated by the traces. And so, say all the nilpotent matrices have the same invariant, namely just 0. So they're in the null code. But still evident that we have different conjugation classes of nilpotent matrices, and they are not separated by the invariants. But we will next time we will prove a theorem of Maxwell-Rosenlicht, saying that there is an open subvariety X prime in X, and G invariant, where the invariants do separate the orbits. So in our running example, this GLN prime is a set of regular matrices. Regular means that, say, their orbits have the maximal possible dimension. Has dimension n squared minus, sorry, n capital N squared minus capital N. And maybe, well, I don't know where to, I don't want to start a new page. In more down-to-earth terms, it means that the characteristic polynomial of A is the minimal polynomial. Okay, so this will be the subject of the next class, and also you will have some problems in home assignment about regular matrices. Okay, so that's it for today. Any questions? If not, I'm saving the lecture notes, and see you next Tuesday. Thank you.